Okay. So as I was mentioning, what we would do is we would wrap up this course with the shape from stereo itself. Okay, shape from structured light. Let's see if there is some light later. We will see that time. But this would be the last topic to discuss here. Okay, so so when we compare with the our initial plan, a couple of topics are now are left. So one is this and other is graph cuts. So graph cuts, as I was mentioning, might cover in other courses, like for example, maybe if third year students, if, yeah, it's again, it will not be a proper computer vision course, but it's a medical image processing, more of medical image processing course. So there I might cover graph cuts. But anyway, you could learn irrespective of that course as well. You have a lot of resources, right? So yeah, let's see if we could finish today. Yeah, that's possible only when all of you have already gone through it. Okay, so otherwise we would just have one more. Yeah, probably that's too much for a single class. If that doesn't work out, let's have just one class. We could even have it tomorrow within this week itself before Sunday, and with that we could wrap up the computer vision course. Okay, so yeah, I will now go through the slides and let's quickly go through. Yeah, it will follow the same flow as the presentation, as the videos of Professor Aaron Bobbick you have gone through. So it will follow, it will be in very similar, almost in the same lines. Okay, right? So let's 1 minute. Yeah, that's fine. So this is shape from stereo. That's what we will go through it. And maybe I will switch off my video as well, so that those who have a bandwidth issue should find it fine. Okay, right. So the name says it's like a one special case. You could see it as a special case of interpreting the 3D shape from multiple views, right? Where you have only the multiple view is in fact just two views. That's the idea here. And this is one of the perhaps the most popular or widely used one is the stereo. Okay, the experiments are very interesting. So more like we all see with two eyes. So in a way, what we do is our stereo, the computer vision, in computer vision, what you do as shape from stereo imitates how we interpret things. So it's natural that you try to see how we interpret things in the first place. So there were very many interesting experiments that have been done. Okay, and one of them is whether we first find patterns and then fuse, or do we first fuse and then find patterns. So hope what I mentioned is clear to you. So fuse is, by that I mean you have two views. So you first, do we first find out patterns and accordingly then we fuse. So if you are finding first patterns within individual image, that's referred to as monocular process. And another is you first fuse images and then you try to find patterns such that, because the pattern shift would tell you disparity in the two images, those of certain patterns would tell you the height information essentially. So that's the basic experiments that people have done it. Okay, I don't want to spend here.
Sir,
Yeah. Yes, Shashwat, you
sir,
are
what exactly, sir, what exactly do they mean by fusing the two images, sir?
yeah, okay, good question. So fusing is, for example, see, that's one of them is from a, maybe this is better. Okay, look at this image. Um, let me go to pen mode. Okay, see, for example, this is, assume that this is the left eye. Okay, you got one image from that, correct? And there is another image that's your right eye is capturing. So is it like fusing is combining them and you don't see two cups, right? When we see it, or whatever you see only single image, correct? That means we are fusing the information coming from the two eyes. That's what we are appropriately merging the information coming from the both eyes, which you could call it as from both cameras if you want. You call it particularly in term, when we are talking in the context of stereo vision. Is that clear what it means by fusing?
Yes, sir.
Okay, right. So one thing is the question that has been posed here is, do we first identify some patterns, okay, and then fuse? Or you first fuse and then find patterns? The answer is, since you have gone through it, some of you have already gone through it. The answer is, do you first find patterns and then fuse, or you first fuse and then find patterns, thereby interpret the height or depth?
We first find patterns.
No, that's exactly obvious. Exactly the opposite we would do. So that this is a very interesting experiment they have done it to prove or disprove this. They took a cube here, okay, and this is one camera C1, camera C2, and they kept a random stereo, so some random pattern they have sprayed on it, okay, they sprayed something, okay, and created a random pattern on it. Then what could be observed is, you in fact cannot see any as such any pattern here in the local images, because let's see, if you have a pattern, then you don't really know what is happening first. So they created a something where you cannot, in a monocular vision, you cannot see any pattern. But the moment these two, see this, we cannot do it here, but again, if you want to do it, you should, like the setup that we have seen in the previous one, you need to separate, you should have a separating shield, okay. On this side you should be showing the like this image should be shown on one side, and this image should be shown on the other side, okay. And you should be here with your one eye here and the other eye here, okay. You should be seeing from in this direction. And then what we would interpret without difficulty is, we would see the cube there, in fact. But if you just individually see it, there is nothing that helps us to interpret it as a cube. So that's what they have, that was the outcome of the experiment that they have done. So this was the thing they were saying: human binocular fusion is not based on matching large scale structures or any processing of the individual images, but would rather your retina and the way it is projected, and then the way it is going to some visual cortex and other things in your brain, okay. By the time already you have a fused image, okay, by the time it goes for your brain to interpret things, and then it looks at the patterns, how much it has moved, and thereby interprets the depth. That's the basic stuff. Okay, so the next question would be, so that's just a question of curiosity, and of course of very important thing is that, that's what we have seen till now, is that in our vision we have a kind of two cameras, okay. Let's not worry, the screen is probably the same screen, you had it, but there were two cameras there, okay. No, screens are also different, no, because each one has its own retina, right? So you have, you could say them as two cameras perfectly, okay. Then in the brain, in the visual cortex, what happens is, it first fuses those two images and then makes them interpretation, okay. So basically, how do you estimate depth from stereo? That's the question. So the shape is estimated based on the motion between two views. So say for example, in this view, say this is what has been there as image one taken. Let's say this is your optical center of this image, okay. You are capturing one image here of a scene point here, and there is another image that you are capturing, okay, at a different angle. So let's call this as I1, and this, let's call it as I2. Then how do we interpret is how much this point has moved. Based on that, the depth you would be interpreting. So any intuition on would you expect for an object which is closer, do you expect in this scenario a higher so this, the term used for this is, instead of saying it, the motion is to give you the motion between the two views is slightly inaccurate, but to make it more clear, that has been given in that way. So the technical word used for it is disparity, okay, which means how much this point, okay, difference between the in number of pixels between these 2 points is what you call it as disparity, okay. The same pixel, you take it here, for example, it might be here. So this distance, how much it has moved, okay, this is, you could see as the corner point here, Okay, this is where your see again some calibration and other things are going on. We will come back to that a little later. But this disparity would tell you how close is the object, or how much is that object closer to you or far away to you. The disparity would tell. Now, what do you think intuitively? Do you think the disparity would be more for an object which is closer to you when you are viewing it from two different viewpoints, or will it be less? The disparity would be less for a closer object which is close to you.
It will be more, sir, for closer.
That's right. That's right. So that's say another thing is you hardly see. You look at the moon. You hardly see any difference with the. You close one eye and see it only with the other eye. You hardly see any difference, right? And the moon, like I think earlier also we were discussing, the moon follows you wherever you go. So the disparity is not there. That object being so far, even a slight movement here would hardly make any difference there. Correct. So on the contrary, you could do it yourself. You keep your pen or something very close to you, okay, somewhere where they have both cameras have access to it to see comfortably, and then you keep on moving and see how much distance it is moving by just looking at your pen only with at a time with only one eye. You would see that as it goes farther, you keep the pen farther and far away, you keep something you keep the pen let's say in a line parallel to your nose, that means in between your two eyes. Okay, then see how it is. The moment you are keeping it close to your eyes, you would see a lot of disparity. Make sense? So that tells it is closer to you. So that's how you interpret how close the object is to you or how far away is the object to you, essentially based on where that, see, our brain is actually, if you are looking at a pen, the cap, the texture, everything, this is making then after fusing it, it is making a matching there, and from that matching it is figuring out where this corresponding pixel is there. Okay, if I could still call it as a pixel for our brain as well. Okay, where that pixel is there in the other image, and that's how we are interpreting indeed whether a object, the 3D shape of an object. Okay, hope that's clear. So yeah, this some math here. Basically, a very simple stereo vision setup here. Assume that you have your point of interest here, okay, which you want to see. The question now is, what is the information given to you? The information given to you is distance between these two uh, cameras, okay, center of projection, or that's you could call it as a focal length, okay, and then yeah, f is the focal length. What do you call it? Center of projection, right? That center of projection is here. Of course, this actually this is there here, in fact, right? This we already discussed. So this f image gets inverted, but that would be mathematically equivalent to having f here. So you kept it there. You know this f value. You know this. You know this b. So with that given, and then in the simplest case, so when you are viewing it, how do you know where this object is? Okay, for example, let me draw here this way. Oops. Okay, this is anyway better is the, I just move on to the next image. You could see here when you are viewing here, you don't really know all this. That could have been a point from anywhere here, is it not? All of them would, in fact, this is your this is the sensor or your image where the image is forming. So any of those points would match here, right? Similarly, when you are viewing it, this point, you could have any of these points could is what you are looking at here. But now assume that you are able to map that this point. Okay, now you see that this whatever point you are observing there is you have it here, whereas on this point you have it here. So now the question is, can with this, so you know what further thing, you know the distance between the two cameras, you know the focal length, okay, from your so this image, you know it what pixel, so this is your center of projection, okay. So from this you would know, for example, you are looking at a point, oops, just a minute, okay, sorry for that, let me come back here. Okay. Hope the pen is still there. Okay, fine. So you know that here this point is there at a distance XL here. This you know. Okay, and you are able to map that the point is same as what you are looking at here. Okay. So the question would be: is this information good enough to tell how far is that point? Okay. So one way you could see is there is one triangle here, and what else? There is another triangle. This is another triangle here. Okay, that's giving a line, but this is another triangle here. Okay, so if you take these two triangles, for example, what is it that I would like to find out is, for example, then let me call this as, let's say, some x1. Okay, and let's call this as x2, and of course x1 plus x2 give me the base thing. So if I write now, for example, this x1 divided by, what should I write there? X1 divided by, I want to write xl, right? So let's say the base of that should be equal, so this and this. Similarly now, since I have written for the bigger triangle first, so here this would be equal to z by what else? Z by f, is it not? So I would get here x1, x1 is equal to xl into z by f. I could do the same thing here. So I let me write it here x2 first. Okay, so this time let me take this triangle, okay, and this triangle. These are two again similar triangles because these two lines are parallel. Okay, and then they're sharing the same hypotenuse. Okay, now if I write here x2 divided by anyone there? X2 divided by
Z.
Yeah, let me write the length of the base itself now. So what should I write there? X2 divided by
XR
minus XR. See here, the notation that we are following, it is assume that the center is 0. This is there towards your left and this is there towards your right. Okay, this would always happen if your object is in between the two cameras. Okay, center of projections of the two cameras. So that's why this has been, I'm writing here minus XR. Okay, that is equivalent to now the bigger triangle Z divided by F. Okay, 1 minute. Can I not go back? Something had happened. Okay, so this is what I got. So that means x2 is equivalent to minus xr into c by f. You add both, that would give you x1 plus x2 is equal to b. That's equal to g by f into xl minus xr. So from that, you know that z equal to b times f by xl minus xr. Is that correct? Okay. Yeah, this has been done there in the presentation slightly differently. Okay, this parallel triangle and this has been taken, but doesn't matter. You could do it in this manner as well. So what is this equation telling you? Can you now relate it to the disparity to the height and tell me the interpretation there?
XL minus XR is the disparity.
Correct. So you know that this is making it a pixel which is there at XL and the other is at minus XR. So XL minus XR is giving you the disparity. So higher the disparity, the Z value is going to be less. So that means Z is less means the object is closer to the camera, right? So that's all. And what about XL and XR when being same, when will that happen? When your Z equal to 0 or Z equal to infinity. So for some object which is going far, okay, that's when if you then you fix Z and take it the other way around. So your G is infinity means XL minus XR equal to 0. Correct? Yeah. So this is the very basic simple setup where you could notice. So you could see here, all I need to give you for a simple stereo system of where the axis of all those two systems are in parallel with your object of interest, right? They're both the axes of the cameras are parallel. Okay, that's all I need to say. Then you could see here the z will be equivalent to the baseline. We call it as a baseline, the distance between the two center of projections multiplied with the focal length divided by the disparity would give you the z value. Okay, so the same thing done here. Okay, this is an image where you are plotting the disparity. The second, so the image on one is on the left and another is on the right. Okay, so this point, if you take it here, that's in fact what is corresponding here, but this has moved here. So that movement is given as, that is how much it has moved, the disparity. Okay, so you could see here, the brighter it is, the disparity is more. That's the interpretation there. Okay, so that's how the plot has been made. So you could see here, of course, this is of course closer to the camera, is it not? This is, the ground is closer to the camera, so you could see here these values being very high. Okay, and then you could see this is coming first, and then as you are moving back, at the back side this building is there. Okay, the same thing you could observe here. This is having a next higher intensity. Okay, a little less than that is this building, and then you could see the trees. Okay, the trees are backside this building, right? From occlusions and all, with a single image we are able to interpret, but now we are trying to enable the computer to do that. So you could see some, of course there are some errors here, but still you could see the trees here, and much farther is the sky here, of course, and then this disparity there is becoming zero. So that's how you could see the disparity map there. Okay, is that clear?
Yes.
Good. So yeah, what we have seen right now is this setup, okay, where the center of projections or the axis of these cameras two are parallel. It need not be always the case, right? You could in fact keep them at an oblique at some angle as well. Okay, they are having some angle, not necessarily parallel lines. That then also it has certain advantages. So you would be doing that, but then the question would be, uh, suppose if I observe a point, so there is a point P here. Okay, so here you could say this might be representing, this is the line. If you connect the center of projection to this and continue that, you could say any of these points might be in, this would represent one of those points on this Z. We don't know where exactly is that point, is it not? Now for this point, let the correspondence be called as P prime. The question that is posed here is, can this P prime be anywhere in the image, or can you say that this can be only in so and so regions, or in or what can we say about, can it be randomly anywhere or no? Is the question clear? So here you have a point P that might be representing a scene at one of these heights. Okay, on this straight line only, this would see, this line, this point doesn't represent, when this is your center of projection, it won't be representing any points here, right? It can only represent one point here from when you are projecting it here. The question now is, while I am looking for correspondence of this point P here, let me call that correspondence P prime. Can it lie anywhere in this image, or are there any specific regions where it is enough for me to look at for this point, is the question. Since some of you have already gone through it, should be able to answer this. So think about the perspective projection there. See, basically each camera is, you are looking at a perspective projection of 3D world into 2D, right? So this camera, what you are getting here also is perspective projection. So what you had to look for this point is, since it might be coming from any of these points, all you need to see is where all these points could map to here, right? Where can they map to? Yeah, some of you should be able to answer this. Can it map anywhere, or where can it map to?
The locus of intersection between the plane and the lines between the point.
Right.
So it's
what would be
another
that?
line on the plane.
That's all.
Another line on the.
Correct. That's all. So basically, a line. This is basically you are looking for a line here, is it not? Where this line gets mapped in the other images, what you are getting are trying to look at. A line maps to a line still. That's the perspective projection properties, if you recollect. So what would happen there is, if you are looking, if this is your center of projection, and all these points, if you draw it, okay, where this could come to, suppose assume that this point is here, okay, and you connect it, this is your center of projection. You take all those points and this would form a single line here. So if you are looking for matching for this point, it's not like you have to look for everywhere, but just simply look at for the correspondences on this particular line. Is that clear to everyone? This is coming from the properties of the perspective projection itself, where a line maps to a line. So all you have to look for is this point would represent certainly one of the points on this line, that is for sure. So this line again maps to a line, as simple as that. So where do you should have to look for? You just simply look at this line here. That's all. Is that clear? And these lines, and now the next question would be this one. This is a very yeah, pay attention here. This is another very important point. Now you take any point here on this line, for example. Okay, so what did we say there? For example, if I am observing something here, point P, it could correspond to any. So you again, you by looking into 2D, you have to you visualize here 3D. Okay, there is no escape from this. So you think of it as here. This is the line going out of this perpendicular to this plane. Okay, hope I'm sure you will be able to visualize that. Now this point, this is intersecting here. Don't think that this is all not on this image. Okay, this is perpendicular. This is just intersecting at this point on the image. But now the question is, the same interpretation, try to do it from this image point of view. Now you observe a point P2 dash here, okay, P2 prime here. Again, that could represent, in fact, could be coming from any of the points here. And for this, where to look for, if you look at it, there will be two lines here. So this is a, you imagine it in 3D. Okay, this is coming how should I say, hope you are able to see it. This in fact is just, this line is going through it, okay, just cutting it at this point, okay, that line, and then that's coming out of outside your away from you. Okay, that's how the plane is coming. And you would figure out that in fact all these points, that intersection of, so there is a plane here you could see, which is formed by connecting these two center of projections that would intersect here at these 2 points. And these are of course, I guess they are called as epipoles. And you would get here, as I mentioned, this point could be there somewhere on any of this line, and you would figure out that for this line, all these points should have a match on this line. Okay, and these two are called as epipolar lines. Epipolar lines. That's what you could visualize it. Yeah, just spend some time with it. Okay, these are perpendicular planes there. These are the image planes. This is how this ray is going perpendicular to this plane. Okay, this plane you see as a vertical plane. This is the plane going towards that, and this is the one which is connecting those two planes. And your image plane is large enough to have an intersection here. Okay, and then this is the line you would get there, right? So all the message here is, if you want to find out correspondences for the points that are there on this line, you simply look at points that are there on this line and vice versa. And these two lines are called as epipolar lines, and this plane connecting the centers of projection with this centers of projection and the world points that you are looking at here, okay, which you get by passing a line here. This is called as epipolar plane, that they call it as epipolar line. Okay, these are epipolar lines. Okay, and these two are called as epipoles. And of course, this is center of projection for the first camera, and this is center of projection for the second camera, and the line connecting them is referred to as baseline. Is it clear so far? This would take a while to make a visualization and interpretation properly, but yeah, just yeah, is that clear? Or you have any quick question here? Just to make sure you understood correctly, let me pose this same question here. Why is this epipolar constraint useful? Why is it useful? Or is it useful in the first place? What is the epipolar constraint in the first place? So this any point here could have a mapping only on this here, and any point here can have a mapping only. Yeah, of course, if any point here is having mapping only here, the other way also it has to be true in a way, right? Because assuming it cannot have multiple mappings, right? So it is helping you with the search space where you have to exactly look for. So thereby it is like this is helping you to avoid some false possibilities of false matching as well, right? Okay, so again, if you have, I guess this is for you do some calibration here. I think this is for two parallel images. Okay, if your center of projections are parallel, what would then why is it useful is, if you want to find out where this point has gone, okay, this point might be somewhere here. If you put it, all you have to look for is search for a matching just on this line, and stop worrying about how big is the image, and where the, of course, this row size would vary, but other columns you don't have to worry. You just have to look on this. A single scan line is good enough for you to search for it. Okay, and same thing here. Suppose you had 4 points here. Okay, this is again, this is where you, I guess, where there is some angle between the center of projections. You want to find out this, you just need to find out the epipolar line for this point, and that turned out to be this. So you simply search at this point. Otherwise, look how many false positives you could end up with, because this all look very similar here. And of course, it's computationally expensive, as well as accuracy wise, it could lead you to a lot of false matchings there. Okay, so same is the case. You want to find out a matching here, you look at the epipolar line, that's going to be here, you just look there. Okay, same is the case here for this point, and for this point, this is the line.
Sir?
Yes, sir.
Sir, instead of two shifted images, like if there are two same images, then there won't be any epipolar line, right?
There is no shift at all, right? That would happen when your z is infinity. You will get that. That is only when you will not have any shift there.
So there won't be any epipolar line there.
Yeah, it's like a people. Yeah, good question. It would actually have it infinity. They will have. It's basically the parallel things. So what would happen? Well, this would go parallel here, something. So there will be. So the question is, if you have the same image, where should I look for the matching? That's the question, right?
Yes, sir.
Let me, yeah, probably you could start from this image to make the interpretation. Okay. Or see, what is it in our control? It's actually, so first question is, when will be the disparity 0? That's the question, correct? So that means,
Yes, sir.
you are saying, you are telling that disparity is 0, basically.
Yes, sir.
Means this is how the point is somewhere here. Suppose if there is a point very far, okay, yeah, I need some time to think about it. I could not immediately do this out. Yeah.
Okay, sir.
Yeah, let me think about it. You also meanwhile think about that. Yeah, it should not be too difficult to figure this out, but yeah, I need some time. Could not immediately answer this question. If the point is close, what is happening here? So the question is, what if the point is very far, right? Somewhere here, let's say. Is it not? The question boils down to, see, basically having 0 disparity is equivalent to looking at a point which is at z equal to infinity. Is it not?
Yes, sir.
So I guess, this is my guess, could be wrong, is that you get parallel epipolar lines. Your lines will be parallel. See, this case they will actually somewhere they will intersect, I think. See, these are they might intersect. See, that might be out of your image plane. I'm just blabbering something. I'm not very sure. See, if I have a point which is very far here, okay, what would happen then?
I think, sir, epipolar lines will not be there. Like there will be epipolar points rather.
My guess is you might have epipolar lines, but that's just that could extend beyond your image also, probably. This is where you are capturing it. Essentially, this is your center of projection. Okay, this is the region where you are capturing it. Is it not?
Yes, sir.
So it is not there just within your region of capture. That's all. The point is.
Okay, sir.
So see, if it's very far, yeah, that's my quick guess, but I need to, yeah, it could be wrong. So please, I'll try to find out an answer, but meanwhile, you also keep thinking about it. I do not have any certain answer right now. I need to still do some, yeah, I need to think about it. That's good. Okay, other than that, any other question here? Yeah, what you would see is when you have some angle here, these lines would come like this. Okay, let me come out of the question you have asked. Okay, yeah, let's continue here. Okay, right. So you will have parallel lines that are right, no oblique line, straight lines. Yeah, of course, those are also straight lines, but here in the same row, you would find out the moment you have parallel cameras. So that's what you would get here. That's what this image tells. Okay, that's so far we have talked about uh, just the locus of points where you could have a matching. So that's all we have seen so far. Okay, and the next part is about, so where are we, 23rd slide. Okay, so far clear. It's like now we are going to look at how to find a matching. That's what you would be doing it. Parallel images, assume same focal lengths. Okay, the assumptions that we made are, we are assuming parallel image planes, right? So yeah, from now onwards, the rest you won't be using the oblique lines. Okay, not oblique lines, tilted lines. Let me call it. It's not a line parallel to your image. Okay, image row. You assume same focal lengths. Assume epipolar lines are horizontal. Assume also, like, yeah, that's a better way to say. Suppose if its position is there at the same y location. Okay, you call this as, again here, when you have parallel cameras, what would happen is, let's call this as x, let's call this as y. You had to see, once this has been given to you, all you have to look at is that same value of y, you need to search it. Okay, this is what would happen once you do the calibration. Also, they do it in a certain way, which we are not going through it. All you have to look at it is at the same y where the x has moved. So as in other words, you will have disparity in just one direction. That's all. This is what would happen by assuming parallel image planes. Okay, once you assume that the focal lengths are same is what you assume. Okay, then in this case the epipolar lines are becoming horizontal, right? That's what we have seen it. Okay, at the same, that in another words, this is again having same y location, right? But still you could end up with we have not converged to any single point so far. All it is telling you is you have a matching to that at one of these points. That's all you have arrived at so far. So that's only the first part of the story. The second part is now to find, so that's what we have done so far, is referred to as a hard constraint, because you are saying there is no other way, it has to be there on the locus would be a line here. You just need to look at the epipolar line. So that's referred to as hard constraint. And then now you need to find out within all those, among all those pixels that are there on that epipolar line, where do you have the correct matching factors. Okay, that you refer to it as soft constraint. Okay, because it could take one of the many values that are there on that line, and depending on the type of model that you are making there, it would vary a bit also. Okay, so these soft constraints would include, for example, how similar it is, how unique it is, what's the order of your points, or how much is the disparity of this point compared to its neighbors, and there are many other such constraints you would be imposing there. Okay, so are you with me? Are you able to still follow? Okay, so assume that this is the point for which I'm starting on the left hand side image. I'm taking one point here and trying to, I know from epipolar hard constraint that it has to be there on one of these on one of the points on that line. So how do you find a match now? So can you tell something, some approach based on what we have already discussed earlier, whatever background we already have? How do you find a match there, for example, to that?
Match-wise cross correlation.
Right, that's very good. You directly went there. That's very good. So you do a patch-wise cross correlation. That's all. This is a very commonly used thing. Okay. Yeah, in this presentation, he has went step by step to arrive at that. Okay. First thing he did is, for example, this is another image that has been considered in that. You want to find out a match for this point. Okay. What he was doing is computing the sum of square difference for just a single point he is doing, rather than taking a patch. But anyway, that's what he would be eventually arriving at. So let me quickly go there with just these steps. So what he is doing is, to this point, sum of squares. So you take every point here on this. Okay, you subtract the intensity of that point with respect to this point, you square it up, and then you repeat. So this is your you essentially, here you are traveling through the epipolar line, and then you are computing that sum of square difference. And of course, in an ideal scenario, you would have that to be minimum, right? Because the point is having exactly the same intensity, so that will be minimum. You would pick that point. So what's the problem doing it this way? What's the disadvantage of doing it this way?
Due to
Using
illumination variations,
yeah,
cause
that's
problem.
correct. So each image, each camera, you are capturing them from two cameras. So one is illuminations variations could be there. Second, even a slight variation in the settings of your camera also, whatever that the gamma values and gamma correction that you are doing or whatever it is, that also could affect you a lot. So as a next step, what he did is he from sum of square differences he has moved to normalized cross correlation. Okay, that would take care of intensity variations. And now suppose correlation should be high, unlike the difference being low. So at that point, suppose if this is again along your scan line, you are moving here, your x-axis is your x, exactly the x here, if I call it this as x. Okay, and then at each this one a normalized correlation with all the points on this line. Okay, that if you are computing it, of course at this point under ideal conditions you will get a normalized cross correlation of 1, and that's how you find this point. Okay, what is the disadvantage of this? Where, when will it fail?
Scales might be different.
Right. So scales might be different.
Yeah.
That's that would fail. And also, no, scales usually that scale variation you won't consider, but would rather if there is any noise could get added up. Even when there is some noise, this gets this will not work out. Okay, slightly noisy image also would screw up the results. Okay, so this is another image from their yeah, some I don't remember the lab name there. Okay, so what they were doing is, suppose you want to, these are the two scan lines. If you look at the intensity profiles of it, they look very nice here. So more or less you could see the correspondences, but not only just correspondences, you could also, for example, observe here the noise causing some problems, is it not? So there is some problem of noise there. Even you compare this versus this, so noise has an impact. So they at those points you will get wrong matches. So to deal with that, what you do is you consider a patch around that point, and then throughout that patch you compute similarly here. For each scan line you consider a patch around each scan line and compute normalized cross correlation over that patch. Okay, so this, it's not just one image during that scan line you are considering, but the whole region here. In fact, you are considering, if this is your point of interest, this might be your scan line, but you would consider above and below also. Okay, for the scan line, for example, and then you do normalized cross correlation, you compute that. Okay, I don't know why it has gone there. Any guess there why it has gone there? Well, there, if your region is small, then it could go there. For example, if there is no texture, then it could go wrongly. Okay, yeah, this explains things better. I think it was the next slide. No, here only. See, if the, for example, if the patch I am considering is able to get some variations here, suppose if the patch is something like this, okay, then there is some black region, some gray region here, and this transition in between is there. So that could find out this match. But if I'm considering there a very small region here, okay, around this patch, then of course it would fail, is it not? So window size plays a very crucial role here, selecting the right window size. So you could also, so that's why you should take in a, if it is too small, what would be the problem? You would lose the neighborhood information. You could end up with the wrong thing. If you take too small thing, it, all these things would, it might even get mapped to any of these points as well. It can get mapped to. And what's the problem if you are taking a too big size of a patch? What would be the problem? Why can't I take a very big patch? Where would I have a problem? What could be the issue if I keep on increasing the patch size of around that point. Hmm?
I think we'll have occlusion, sir.
That's right. Good. So when there is a, see, the moment you are doing it, for example, so for, let's say you observe this part here, for example. Oops. You observe this part here. Okay. The moment your camera is moved this side, you won't get that part clearly here. Is it not? Do you observe that? So similarly, you could have certain regions will be visible. So the moment you are taking a big patch here, that let's say a patch around here. So this point, assume that you are trying to find out a match. And if your patch is too big, then it would say that this is not getting matched, right? So there is the trade-off because of occlusions and also field of view. Of course, that would also result in a way occlusion. So this is a good example of considering a bigger patch versus a very small patch, with two extremes of the cases. Okay, here for example, for computing the normalized cross correlation, a window size of 3 by 3 is taken. Here a window size of 20 by 20 is taken, or maybe I'm not sure whether this 3 is from the center. Yeah, there will be two ways of writing, but anyways, for us qualitatively, large window and small window is good enough at this point. So what are your observations here with a small window? Or large window, can you tell me where is it, why is it failing, or where is it failing?
For closer objects, it's failing.
So you could see it's more uniform. So yeah, for example, for this tree, one thing you could observe is there are these leaves here, okay, which are like before this trunk, these leaves are there. Okay, so this is actually a bit closer than this trunk, or those branches of the trees. Okay, those things you could get here, but those details are missing the moment you are taking a bigger thing here. That's missing. On the contrary, other thing that's happening when you are taking is, so that's kind of advantage you could see with the smaller window. But the disadvantage that you could observe there is you are ending up with too many spurious results there, very wrong matches, because the matching could go wrong now, because these area, when you consider a very small area, that could look very very too many matches would be there, because it's something like a corner detection in a way. See, finding out matching here, you could correlate it with the whatever we have done with the corner detection. Only when the patch you are considering has a textural variations, you could find out a more appropriate match there. Okay, so those are the two things. Okay, and one window large enough to have sufficient intensity variations. So that's what, by intensity variations, what I mean is very similar. I'm saying it as a textural variation should be there within the window you are considering. It's small enough to contain only pixels with the same disparity. See, the moment you are taking one box versus other box there, what you are essentially doing is you are trying to assign, saying that these two block within this block, you are looking the match there. You're essentially assigning the same disparity, as if these two blocks are having same disparity, you are considering it. See, that's why you would see here patches, okay, than looking at any finer variations. And this is an extreme of finer variations where you have too many spurious things, okay, because it is not able to have sufficient intensity variations within that block, and this is clubbing too many things into a single block. Okay, hope that is clear. And again, as Professor Arun Bobik rightly mentions in his video, this is always a tough problem to deal with. There is no simple answer on how do you choose. If you ask me, how do you choose the right window size? That's always a tricky question. There is no trivial answer for that. Lot of things it depends upon. So is it clear? Yeah, this has been 1 hour. Hope you still, do you want a break? Do you have any class after this? So anyway, there are not many students. Let me just come back and see how many are. Okay. So since it's one, I'll make it just pause at least in the video recording. I'll make it, otherwise it would be too big to upload also. So let me stop recording here. Okay. So let's stop this recording here and we would start with the next one.